All right, carrying on with composing trig functions and inverse trig functions. This time we're going to make it so that the functions don't match, but we're still going to have one of them be a trig and one of them be an arc trig or an inverse trig. So here I've got sine of arc cosine of 1/2. Let's say we just want to evaluate this. We're going to start by evaluating the inner function, arc cosine of 1/2. What's that? Well, being arc cosine, we want to find 1/2 on the x-axis. There's 1/2 on the x-axis, and then we want something in this range. So trace up to the point on the unit circle in that range, and then the question is, what is that angle? What's that angle there? If you remember the unit circle, you'll know that is pi over 3. So sine of arc cosine of 1/2 is going to be the sine of pi over 3. Okay. And then sine of pi over 3 is going to be like taking pi over 3, take this point here, and instead of tracing back down to the x, we're going to trace over to the y. And that right there, that y coordinate, you may recall, is square root of 3 over 2. Again, that's from the unit circle. If you remember all those common angles and their coordinates. So this is square root of 3 over 2. So there we go. You work your way through the composition by evaluating the inner one and then evaluating the outer one. Okay, so that's not too bad. Let's look at something more interesting. Let's say we want to simplify one of these compositions with a variable inside it. Let's say we want to simplify cosine of arc sine of x. Let's just do that. Cosine of arc sine of x. All right. Well, first of all, this is valid only for x values that are between -1 and 1. So first of all, we better have that be the case. We better keep that in mind. Valid only for x values between -1 and 1, because arc sine isn't defined outside of this domain. But now, how can we figure out what that's going to be? Well, there's an approach to this that involves drawing triangles and doing a little bit of sort of geometry reasoning. So let's take this inner function, arc sine of x. Remember that should produce an angle as an output, right? Whatever value that gives us as an output can be interpreted like an angle in that domain, in that range, negative pi over 2 to pi over 2. So let's let theta equal arc sine of x. Okay, I'm just introducing this variable theta to represent that angle output from the arc sine function. Then, if that's true, sine of theta must equal x, right? Sine of theta must equal that x input value. So what we can do now is draw a triangle and put theta as one of the angles in that triangle. And then what we need to do is now label the sides of the triangle such that the opposite over hypotenuse will equal x. There's more than one way to do that, but the easiest way to do it is to put x here and 1 on the hypotenuse. Because now the sine of theta is opposite over hypotenuse, which will be x over 1, which is x. So all I've done is I've created a triangle that has an x coordinate, that has an angle with a sine value equal to x. Now, what you may ask is what would happen if x is a negative number? We're not going to worry too much about with x being a negative number for the moment. We'll get to that possibility in a minute. So the next thing to do is to ask, if we're looking for cosine of this number, we want to know, what is cosine of theta, right? Because our arc sine here is being represented by this angle theta, right? Arc sine is theta. So what's cosine of theta? That's the question. To determine that, we need to do adjacent over hypotenuse, right? But we don't know what adjacent is. Let's call this adjacent coordinate here y. We don't know what y is. But what we could do is figure out y in terms of x by using the relationship between the side lengths of a triangle, of a right triangle. That would be the Pythagorean theorem. So what we can do here is x squared plus y squared should equal 1 squared. And then the y squared is going to be 1 minus x squared. And so y is going to be plus or minus the square root of 1 minus x squared. Now I put a plus or minus because, when you take a square root, you have the two possible solutions. If this really was like an actual right triangle, then we should take the positive one because y is a length. But since the right triangle is more so just like a sort of a geometric construct to help me to help do some reasoning. In reality, that number might actually be negative. So we're going to keep in mind that it could be negative, and we're going to put the plus or minus there. So now cosine of theta is going to be adjacent over hypotenuse, which is going to be this plus or minus square root of 1 minus x squared over 1, right? So I've pretty much got what cosine of theta is going to be. It's going to be that. And so that means that this expression I started with simplifies to plus or minus the square root. No, the divided by 1 doesn't need to be there, so it's really plus or minus the square root of 1 minus x squared. This simplifies to this. But we can actually figure out in this situation whether it should be a plus or a minus. And the reason we can figure that out is because we know what the range of arcsine is, right? So let's go back to the unit circle. Arcsine, whatever x value you give, as long as it's between -1 and 1, arcsine is going to give us something in this range, right? That's what the output is. So theta is somewhere in here. So the question is cosine going to give us a positive or a negative number as an output? Well, I mean, on this range, no matter where you are, cosine is going to be positive, right? It doesn't matter where we are within this range, even if we're at one of the endpoints, cosine is going to be positive, or at least not negative, right? It might be 0, but it's not going to be negative. So because of that, we can actually conclude, our final answer here will be that this cosine of arcsine of x is definitely going to be the positive square root of 1 minus x squared. And we did it. This is called simplifying, right? Like normally simplifying uses things like factoring and canceling and like combining of like terms and all that kind of jazz. Simplifying compositions of trig functions, though, is a whole different ballgame. But you are able, in some cases like this, to take a composition of a trig function and an inverse trig function and simplify it into an algebraic function, which on some level is like mind-blowing, because so far trig functions are not connected in any way to algebraic functions, right? They seem completely alien and completely unrelated to algebra, right? But it is the case from, basically because of things like the Pythagorean theorem and this idea of ratios. Via this reasoning, we can say that this cosine of arcsine of x is equal to, in value, to the square root of 1 minus x squared. And if you go and graph y equals this and y equals that, if you graph those on Desmos, you will discover that they are the same graph, which I still, thinking about that still blows my mind, even after years of teaching it. So there we go. This, by the way, this process of doing this type of thing, this is pretty useful in calculus. So it will come back, and you will use it occasionally over the next few years if you continue on.